Hello folks, my name is Tim and welcome back to my channel. So this is the next installment in the Making a Maker channel series, and it's a continuation of the previous video where we started building a robotic camera operator. So the plan for this video then is to finish up that project by building the remaining element, the turntable. Once we've done that, we'll actually use it to shoot some footage, so that should be quite interesting. Let's see how it goes. Alright, let's take a look at the parts we're going to need to build our turntable then. So first of all, we have these two pieces of 15mm aluminium extrusion. This is a T-slot extrusion, and it's called that because in each of the four sides of this thing there is a little T-shaped slot, and that's very useful for fixing things to the extrusion. And you also have a little threaded bolt hole on the end there. So that's very useful. This stuff is pretty easy to get hold of and forms the basis of quite a lot of projects like this. So into that bolt hole at the end, we're going to fix these four legs, one on the end of each piece of extrusion. So they'll fit on like so. And that's going to lift the extrusion up off the surface of the desk or whatever it's sitting on high enough so that we can suspend a stepper motor underneath it and it won't catch on anything. So that's how that's going to work. In addition to the legs, we have these two sort of flat, squarish cross pieces. Now these are going to fix to the top of the extrusion by fixing into the T-slots. To fix into the T-slot, you use, unsurprisingly, a T-nut. I've got a few of them here. This is a T-nut. Now you can buy these things pre-made in metal or whatever, but if you've got a 3D printer, you can just print your own, and these work very effectively. So it's just a sort of little wedge shape of plastic there, you can see, with a recess on the one side to fit, in this case it's an M3 nut, but you can get them in different sizes. So you just fit your nut into the recess, and then voila, you've got a T-nut, and that just slides into the extrusion channel like so. There you go. And then you can put whatever you want onto the top of this thing, or the side, or however it's oriented, screw down the bolt, and that'll clamp in place and won't go anywhere. So by using four of those T-nuts, we'll fix this cross plate to the top, and then the robot arm itself will sit on top of this, mounted in these four holes here. And fix once it's fixed to the extrusion, it's not going to go anywhere. It's not going to slide or move around. It'll all be nice and rigid. Right. So in addition to that, we also have this similar looking piece. Again, this just screws to the top of the extrusion at the other end, and this is the base of our turntable spindle. It's designed so that it can bolt to the top of the stepper motor. So this fixed to the extrusion, the stepper motor hangs down underneath, screwed on in these sort of four holes. And these are countersunk, and we're going to use some countersunk bolts to fix it, because once they're tightened down, they will sit flush with the base of this little, this sort of ringed recess that's in the top of this part. And that recess is very important, because what that's for, that's actually to hold half of a thrust bearing. So in this project so far, we have used a few bearings in the robot arm, but those bearings were these sort of typical bearings like this. These are the standard common ball bearings you'll see all over the place. And these guys are very good when the direction of the forces acting upon them is perpendicular to the axle that they sit on. So what that actually means is, if you imagine an axle, this bearing was threaded onto an axle that was sticking straight up out of the desk here, then if all of the forces acting upon the bearing are perpendicular, that is at 90 degrees to that axle, then that's the correct application for this bearing. If the forces are coming parallel to the axle, that is straight up or straight down, then this bearing isn't going to be very effective in that situation. It could bind or fail or even get destroyed if the forces are strong enough, but it's not designed for that. If you have that kind of situation, then what you need is a thrust bearing. I've got one here. Take a look. So the first immediate difference you notice, apart from the size, is that this comes in three parts. So you've got a base plate, you've got a little carriage of little cartridge of ball bearings here, and then a top part, and they fit together in a kind of sandwich, like so. And the two parts can turn very freely, but these sorts of bearings are designed for applications where the force is either coming, in this case, straight up or straight down, but parallel to the axle that the bearing sits on. So how are we going to use it? Well, this base part here is just going to fit down inside of that recess, which is why the bolts need to be flush with the surface. And that will then screw to the top of the stepper motor, like so. And that will form the base part of the turntable spindle. The little carriage of ball bearing sits on next. And finally, we have this top, which similar sort of design. The bearing ring just sits inside of the recess, and that then fits on top of the whole thing, like so, and gives us the spindle upon which our turntable can rotate, sort of nice and freely. The turntable itself will be a bit bigger than this. This is just the base parts, and the turntable will, a larger ring of material will be fixed on with these 4 bolt holes here. But yeah, that's basically the design of it all. So there we go. All right, let's go build this thing. All right, that's got the base frame built. Nice easy build, everything went together as expected. The T-nuts were a little bit fiddly to line up and slide into the extrusion channels, but once I got everything lined up, it went together quite nicely. The stepper motor has been put in place, that's just there underneath. And the legs are nice and sturdy, so they hold everything, you know, that's not going anywhere. The bearing ring is sitting in its recess. That's a nice snug fit. So yeah, that's all gone together as designed. Lovely. But we do have one problem, and that's this part here. Now, when I printed this part, I actually used a feature of my slicer that I haven't tried before. Normally, when you make a 3D printed part with any bolt holes or whatever in it, those holes will come out slightly undersized. And that's because the 3D printed filament has a tendency to expand. So if you print a 2mm radius hole, you'll get a slightly smaller, sort of 1.9 or 1.8mm hole as a result. Now, that could be a problem if your bolts don't fit through, or you need pieces that fit together nicely. You can counter this by, in your CAD design, actually oversizing your holes a little bit. But that's not really the right way to do it, although it's what I've tended to do in the past. The reason that's not correct is because if you take the same CAD design and you print it on a different printer or with a different filament, you may find that that filament or printer has slightly different expansion tolerances, and your oversized CAD model is now actually too big or too small. So it's not the right way to do it. The right way to do it is to let your slicer take care of the problem. And in your slicer, you should have a setting for hole expansion. And in there, you can program an offset, either a negative or positive, depending on if your holes are too big or too small, size in fractions of a millimeter, and the slicer, when it creates the G-code for your printer, will take care of oversizing the holes for you. That way then you can create different profiles for different printers and different filament types, and the expansion levels can be adjusted accordingly. Anyway, I'd never played with it before, so when I printed this part out, I actually oversized the holes just a little bit too much. The center hole in here is supposed to be a snug fit on the shaft of the stepper motor in order to grip so that when the stepper turns, the turntable goes with it. Unfortunately, it isn't. As you can see, that's a very loose fit on that stepper motor shaft, and there's no way that that's going to work. But we don't need to scrap the part. We can actually fix this relatively easily. And all we need is a small piece of paper. So take the paper, maybe fold it over perhaps, it depends how much you actually need to fill in, and then just roll it into a little tube, like so, and poke that down inside the oversized hole. And what that's going to do is it's actually going to take up the space, so effectively making this hole just ever so slightly smaller, and that should then fit onto the shaft of the motor nice and tightly as we wanted in the original design. So let's try it. All right, so that has worked. That's a nice tight fit on there now. The paper's a bit long, I'll need to cut that down, but you get the idea. So sometimes if your holes are just ever so slightly out of dimension, this little trick can save you having to reprint an entire new part. Probably not a good idea for anything that needs a lot of torque or anything that's very precise, but for this application, sorted. So now that we've fixed the slight issue we had with this part, there's one final thing we need to do before we can assemble the turntable, and that's greasing this bearing. So these open bearings, multi-part bearings, best to put a bit of grease into these things just so they run smoothly. You're not really supposed to run them dry. So I've got this bearing grease here. I don't really know a lot about bearing grease, and I certainly haven't used this particular stuff before, so let's give it a go and see what happens. So to apply it, I'm just going to use a little plastic cap to act as a tray, and I'm going to squeeze a little bit out. Now, I would follow the instructions for this stuff, but they're in German, so unfortunately, I don't understand what they actually say. But let's see if we can't figure it out. Okay, so to apply it, I'm just taking a little brush. I'm just going to brush it onto the bearing rings where the ball bearings will sit, and that should be sufficient. So let's do that. Right, that should do the trick. The next thing we need to do then is to take the turntable hub here and attach it to a larger circular plate that we can use to give it a bit of extra size. Now, I had a look around to see what I could find to do that, and given that we're still in COVID lockdown, my choices were limited. But what I came up with is this. This is a cake board. It's a pretty sturdy, solid piece of material. I put some holes in so that we can bolt it down to the fixings here. And to do that, we need to find the center of this thing. Finding the center of a circle like this is not that difficult, actually. There are a few different ways you can do it. But what I'm going to use is one of these. This is a center finding jig that you can use to find the center on any reasonably sized circular object. It's 3D printed. It doesn't take very long to print. It's very simple and yeah, a useful little thing to have in your toolbox. So how you use it, you just butt it up against one edge of the circle, and then you draw along the straight here, and that will, it'll give you one reference line. You then move it about a quarter rotation, and you draw again a second line. Where those two lines cross, that's your center point. Simple to use. There you go. Okay, so that should be the center point. So now that we have that, all I need to do is to mark off the distance from the center where the screw holes will go and then drill it. Right, that's got that attached. Did not quite go to plan, unfortunately. I had hoped to use some nice countersunk bolts that I've got, but they were not long enough, unfortunately. So I had to switch to these regular bolts. It's a bit of a mess, but well, it'll do for now, and I'm going to improve this and replace it with something better long term. And here we go. This is the finished item. So I've just attached the robot arm that we built in the last video to the opposite end of the turntable bed, wired everything back up, and I'm just putting it through its paces now. As you can see, we've got some really nice smooth motion out of it. In the previous video, we'd made the robot arm move, but the motion was very jerky and the motors were very loud. To solve that, I actually just enabled micro-stepping on the stepper motor drivers, and that resulted in much quieter movement and much smoother, more controlled movement as well. This is set to 32 times micro-stepping. That might be a bit much, but so far it's looking pretty good. So yeah, I'm very happy with this. The movement is good and we should be able to get some nice footage out of it. But before we can see what that's going to look like, we still need to put a camera on this thing. So let's talk about cameras then. So this is a Raspberry Pi 3B. I use this to control my 3D printer. It runs Octoprint, and connected to it via this ribbon cable is a Raspberry Pi camera module V2. It's a very little board, you can see, and attached to it is an even smaller camera sensor. If I put my thumb there for a scale, you can see this is a really tiny little camera with a very, very minuscule little lens in front of it. Now, it's okay. It's not terrible. I use this to shoot time-lapse footage from my 3D printer, and it works okay for that sort of thing, but it isn't a really very good camera. We've invested a reasonable amount of effort in this project so far, and it seemed kind of silly just to use an inferior camera like that and spoil it. So what I did instead was I went out and I got one of these. This is a little bit more like it. You can see there's a few boards here. This is a Raspberry Pi camera module high quality, the HQ camera module, and connected via this little plastic plate is a Raspberry Pi 0W. The W part doesn't really matter, we're not using the Wi-Fi, but that's what I had on hand, so that's what I used. And that's connected via a slightly different ribbon cable here, but essentially it's the same idea as in this example. The really important thing about this, though, is this lens. The high-quality camera module allows you to attach interchangeable lenses, and that makes a huge difference. So as well as being a more capable camera just in general, you can get some very nice lenses for it. So on here I have a varifocal lens by a company called ArduCam. This is very nice. This will let you adjust between a telephoto lens and a wide angle lens. It's basically a zoom lens, as well as controlling the aperture and the focus via these slider rings. So very, very nice lens. And you can get a few different lenses for the Raspberry Pi camera module. I've got a few here. This is the standard wide angle lens. That's the official 6mm wide angle. And I've got the 16mm telephoto lens as well. And all these can be swapped in and out onto the high quality camera module. So you can adjust the lens to best suit whatever it is you're trying to film. So this is really, really good, and a lot more like it. I mean, if you look at the size difference between the, the minuscule little lens there and this piece here, you can clearly see this is a much more serious bit of kit. So let's get this fitted to the robot arm and finally record some footage with this thing. Well, all right then. We're not going to win any awards with that. The footage is very wobbly and shaky with lots of jerkiness and all sorts of problems. It's okay, and as an idea, I think this is still going to work, but the main problem seems to be the weight of the new camera module. It's certainly more capable, but it's also significantly heavier, and that's a problem. The motors, well, they're powerful enough to shift it without any real issue, but the structural elements, the mechanical parts of the robot arm are just not up to it. There's a lot of slop and wobble and wiggle in all of the joints, and that shows up as jerkiness in the footage. So we're going to need to redesign it. I think the idea here is good, but we just need to optimize the design of the arm. Maybe come up with something a bit simpler, something with a fewer moving parts. That's probably going to be our best bet for success here. Anyway, I think that's quite sufficient for one video, so cheers, and thanks for watching.